What if we covered the moon with solar panels? Imagine looking up at the night sky and seeing not the familiar silver orb of the moon, but a faint glimmer, or perhaps a grid-like shimmer, across its surface. This isn't science fiction for the sake of fantasy. It's a thought experiment that combines engineering ambition, limitless energy, and the scale of cosmic possibility. What if we covered the entire surface of the moon with solar panels? Let's explore, step by step, what such a radical idea could mean for humanity, Earth, and our shared future. First, consider the moon itself. The moon is a rocky satellite, locked in synchronous rotation with Earth, always showing us the same face. Its surface area is vast, about 37.9 million square kilometers. For comparison, that's close to the land area of North and South America combined. Most of that area is uninhabitable, cratered, dry, and exposed to the harshness of space. But it also represents an unbroken expanse, free from weather, human cities, and atmospheric interference. Despite its hostile conditions, the moon receives an abundance of sunlight, about 1361 watts per square meter on average, practically the same as at the top of Earth's atmosphere. Solar panels work by capturing sunlight and converting it into electricity. On Earth, their efficiency is challenged by clouds, weather, nighttime, and the filtering effect of our atmosphere. But on the moon, with no atmosphere and 2 weeks of sunlight out of every lunar month, each panel would get much more unimpeded exposure. So, if you covered the whole lunar surface with top-tier solar technology, the amount of energy harnessed would be astounding. How much energy? Let's crunch the numbers. With its 37.9 million square kilometers, and assuming cutting-edge solar panels with an average efficiency of about 20%, we can calculate the moon's potential output. First, 37.9 million km2 is 37,900,000 square meters. Multiply that by 1361 watts per meter squared, and you'd have roughly 5.16 watts, or 51,1600 terawatts, arriving at the lunar surface whenever it's illuminated. With 20% efficiency, the panels would generate over 10,000 terawatts of continuous power while in sunlight. To put this in context, the entire world's population, cities, industries, and technologies consume about 20 terawatts at any given time. That means such a lunar solar grid could outproduce present human demand over 500 times. In other words, this lunar solar network could supply all of Earth's needs many times over, with energy to spare. But before we get carried away, let's examine what it would take to make such a dream a reality. The challenges begin with manufacturing and transporting the solar panels. At present, solar panel factories on Earth are measured in the tens or hundreds of thousands of square meters. Even with exponential growth, building enough panels to cover the moon would be an industrial endeavor many magnitudes beyond our current capabilities, requiring advanced robotics, automated assembly lines, and continuous transport, not just from Earth, but perhaps even from lunar sources. This brings us to the concept of in situ resource utilization, using the raw materials already on the moon. The lunar regolith, or the layer of loose dust and rock covering the surface, is rich in silicon, the element at the heart of most solar cells. Rather than launching vast quantities of panels from Earth's deep gravity well, it would be essential to build solar panel manufacturing facilities right there on the lunar surface, mining, refining, fabricating, and deploying everything using machines, mostly operating autonomously. Such an undertaking would be an unprecedented leap in engineering, launching fleets of robots and construction bots to the moon, establishing mines, foundries, chemical processing plants, glassworks, and precision assembly lines, all functioning in vacuum, extremes of temperature, and constant bombardment by cosmic rays and micrometeorites. These facilities would need the ability to repair themselves, replace parts, and keep expanding the solar grid outwards, tile by tile, until millions of square kilometers were covered. The panels themselves would need to be ultra-durable. Unlike on Earth, each panel would be exposed to frightening extremes. During the lunar day, surface temperatures can soar to over 120 degrees Celsius. At night, they can plunge to minus 170 degrees. There's no air, so heat can't escape except by radiation, and the lack of atmosphere means every panel would endure the full onslaught of solar ultraviolet rays and cosmic rays, radiations that degrade materials and damage electronics. Dust is also a pressing issue. The fine abrasive lunar regolith, kicked up by micrometeorites or static charges, would settle on panel surfaces, blocking sunlight and reducing efficiency. Self-cleaning, perhaps using electrostatic repulsion or robotic brushes, would be necessary to keep them operational. Then there's a staggering logistical challenge, covering both the near side, the hemisphere facing Earth, easily visible from telescopes and communication stations, and the far side, hidden from direct radio contact with our planet. The network of solar panels would need not just power generation capabilities, but also infrastructure to store and transmit this energy. Here lies another critical issue. The Moon's day lasts about 29.5 Earth days, meaning every 2 weeks it is in total darkness. For half of each lunar cycle, solar panels on the night side would produce nothing. A complete global grid would thus require massive energy storage solutions, such as advanced batteries, supercapacitors, or another method to bank the sunlight from each long lunar day, and somehow even out the supply over the long, freezing night. Alternatively, an energy transmission system could shift power from sunlit panels to the night side, but across 3,500 kilometers of harsh, cratered terrain, this would be a feat of engineering. Transmitting the energy from the Moon to Earth is another profound challenge. Directly connecting the Moon's electricity to Earth's grid with wires is impossible. The distance is hundreds of thousands of kilometers across the vacuum of space. Instead, some propose wireless energy transmission using dazzling new technologies, most commonly either focused microwave beams or tightly collimated lasers. Envision enormous transmitting stations dotting the lunar surface, each converting gigawatts of electricity into powerful microwave beams, targeted precisely at receiving arrays, rectiniforms, on Earth. The receivers would convert the microwaves back into electricity, feeding it into the grid. Such a system would require pinpoint accuracy, advanced safety protocols to prevent harm to wildlife or aircraft, and robust line-of-sight alignment, accounting for the Moon's orbital motion and Earth's rotation. There would also be concerns about energy losses during transmission, although with advances in focused beaming and rectification, these might be kept manageable. Now, imagine the geopolitical and infrastructural implications. If all of Earth's energy comes from a single artificial moon grid, control over this resource would be an immense strategic asset and a potential cause of conflict. Managing access, allocation, and maintenance of this immense power source would require unprecedented international cooperation, with robust treaties to prevent monopolization, sabotage, or accidental disruptions. But let's pivot to the benefits. With effectively limitless clean power fed to every corner of the globe, the age of fossil fuels, coal, oil, and gas, would end. Pollution from vehicles, factories, and power plants would dwindle rapidly. Carbon dioxide emissions would plummet, likely stabilizing or even reversing the effects of climate change. Remote villages, isolated islands, vast deserts, and Arctic outposts could all have guaranteed access to abundant electricity, opening new avenues for progress, education, prosperity, and quality of life. With an oversupply of power, industries once throttled by energy costs, such as desalination, water purification, nitrogen fixation, aluminum smelting, and carbon capture, could be run at scales that today's economies cannot afford. We could synthesize fuels from air and water using surplus electricity, rendering fossil fuel extraction unnecessary. Minerals and metals could be produced cleanly, cheaply, and abundantly. Huge quantities of fresh water, hydrogen, and synthetic food ingredients could be made in powered facilities, feeding billions. Space itself would become more accessible. With gigawatts to spare, electromagnetic launch systems could catapult payloads to orbit, or even power interplanetary travel. The infrastructure built to create and maintain the lunar solar grid, robotic construction, mining, advanced materials, could be extended to asteroids, Mars, and beyond, turning the moon into a staging ground not just for power generation, but for all manner of cosmic industry. Globally, societies would be transformed. The new abundance of power would lower costs, removing one of the great bottlenecks for civilization. Clean, cheap energy could drastically reduce poverty, improve health, and foster equality. Rural electrification would leap ahead, bringing light, refrigeration, and digital connectivity to the most remote communities. Global communication, data centers, AI, and cyber-physical systems could expand without limit. It's inevitable, however, that such a massive technological leap would introduce unexpected side effects. For instance, the transmission of thousands of terawatts through microwaves or lasers, unless carefully managed, could affect the Earth's upper atmosphere or incidentally harm biological systems. The constant, intense beaming of energy might require dedicated no-fly zones, wildlife refuges, and stringent regulations to protect people, animals, and satellites. And what of the moon's appearance in the night sky? The moon today is an object of cultural wonder, inspiration, and myth. A silver lantern grounding us in the cosmos. Plastering it with reflective panels would alter its visage, perhaps replacing familiar craters with irregular patterns, or even causing it to appear darker or shinier depending on the light. For astronomers and poets alike, this would signal the end of an era, as one of the last untouched wildernesses of the solar system becomes a site of perpetual construction and artificiality. Beyond the technical and aesthetic changes, there are environmental concerns. The lunar ecosystem, while not teeming with life, is a fragile geologic history preserved in slow motion for billions of years. Blanketing it with machinery could obscure or damage important scientific sites, erasing crucial records of the solar system's formation and development. A more subtle risk involves the waste heat. Even with perfect efficiency, transmitting vast quantities of energy to Earth inevitably increases our planet's total heat load. Today, incoming sunlight is balanced by reflected light and outgoing infrared radiation. If we supplement this with trillions of watts beamed from the moon, over decades and centuries, it could raise planetary temperatures, albeit to a much lesser extent than unchecked fossil fuel burning, unless offset by equal energy usage in ways that do not generate heat, such as splitting water into hydrogen and oxygen for space launch fuels, or investing in outward radiation management. Still, many of these issues remain theoretical, tiny compared to the extraordinary challenges of constructing, maintaining, and controlling an artificial solar array covering an entire world. It's a scale that dwarfs any human project. Millions of square kilometers, hundreds of billions of tons of material, fleets of self-repairing robots, and competing interests between nations, corporations, and cultures. Yet, the idea is more than fantasy. Versions of this concept exist as proposals in the field of space-based solar power, beaming energy from satellites in Earth orbit, or lunar ring projects proposing equatorial bands of solar panels on the moon. Even partial implementations, covering a fraction of the lunar surface, would offer gigantic increases in available clean energy. Such projects inspire the imagination, challenging us to think in terms of planetary engineering, cosmic resource use, and our ultimate destiny as a species. There's also a psychological dimension. The transition from an age of scarcity, where energy is contested, rationed, and geopolitically leveraged, to one of abundance would disrupt social norms, economic structures, and even individual ambitions. What happens when energy, the cornerstone of modern development, becomes cheap and inexhaustible? Will it unleash innovation and prosperity, or increase inequality between those who control the lunar infrastructure and those who depend upon it? Will new environmental threats emerge from the large-scale transformation of the Earth-Moon system? And how will we come together, as a global civilization, to manage the risks and rewards? Historically, each great leap in energy availability, from fire to agricultural biomass, from coal to oil, from fission to renewables, has brought both opportunity and peril. If humanity could muster the will, the resources, and the unity to build a lunar solar array, could we equally develop the wisdom to distribute its fruits equitably and protect the natural wonders we hold dear? To reflect on what it would mean to cover the moon with solar panels is to explore more than engineering. It is to imagine the trajectory of civilization writ large, a dream of energy abundance, cosmic industry, transformed landscapes, and societies. It forces us to confront our potential for both creation and destruction, our longing for progress against our reverence for what is wild and ancient. In summary, covering the moon with solar panels is a breathtaking vision. The technological hurdles are virtually unprecedented, but not unthinkable with continued advances in robotics, material science, manufacturing, and energy transmission. The rewards would be gigantic: clean, inexhaustible energy for all of humanity, and a pathway to further space exploration and settlement. But the risks and side effects, environmental, cultural, societal, demand careful stewardship. Ultimately, this idea pushes us to ask big questions. How bold can we be in shaping our environment, here and out among the stars? What kind of civilization do we want to become? And are we ready, as a species, to undertake projects of such immense scale, striving for abundance while honoring both the worlds we transform and the heritage we inherit? Every time you look up at the moon, imagine what it might someday signify. Not just a pale companion circling our globe, but a testament to the unity, ingenuity, and reach of human effort, or a cautionary tale of overreach and unintended consequences. The future, as always, is a canvas. The brush is in our hands, and the universe is vast enough to hold our largest dreams.